Okay, so this is a lesson on titrations. Okay, so titration is what it's used for is if you have a unknown concentration of, say, an acid, you can use a known concentration of a base in order to determine the concentration of that unknown. And the reason you can do that is you're going to add in this case, the acid, or sorry, you're going to add the base to the acid, and eventually they're going to reach what's called the equivalence point. And that's the point at which you have chemically equal concentrations. For example, you have equal amounts of hydroxide and H plus ions. So this is what a titration curve looks like of a weak acid and a strong base. So if it's a weak acid, it's going to be down here, maybe around 1, 2, 3, 4, 5, 6, something like that. And what happens here is we have sodium hydroxide. Okay, so what happens is we start adding sodium hydroxide down here, and what happens is the pH rises, and eventually it's going to reach what's known as the equivalence point. And again, that's when you have the same quantity of hydroxide and H plus ions, and they neutralize one another. Okay? And notice it has a fairly large shift here. Notice the equivalence point is not, for a strong base, is not at 7. Notice it's over here on the higher pH side, and that's due to the strong base. So the curve of a weak acid and a strong base, the equivalence point is going to be reached somewhere above the pH of 7. This would be a titration of a strong acid with a strong base. And again, what happens is you titrate it. So basically you add the sodium hydroxide to it until it reaches the equivalence point. Notice it's a strong acid with a strong base. The equivalence point is right here at neutral. How would a strong acid with a weak base look? Well, the equivalence point would be somewhere down here on the acid side. Here would be an example of mixing sodium hydroxide with acetic acid. Acetic acid is a monoprotic acid. These hydrogens are covalently bonded, so water can't break them apart. This is the only hydrogen that can be released. So notice it's just a 1-to-1 ratio. So for every 1 mole of sodium hydroxide we add, we can neutralize 1 mole of acetic acid. Now, how do we know when we get to that point? Well, we use an indicator. Okay? And in this case, we're going to use phenolphthalein. What's going to happen is it'll change colors once we reach that point at which they're chemically equivalent quantities. So here's a little titration practice. So it says determine the concentration of 10 milliliters of acetic acid, which is weak acetic acid of vinegar, which reaches the equivalence point when titrated with 1.89 milliliters of a 1 molar NaOH solution. So basically what it's saying is you have 10 milliliters of your acid, you add sodium hydroxide, your strong base, to it until it reaches the equivalence point. And it took 8.9 milliliters of sodium hydroxide. So here's what we're going to do. Go to our mole floppy. So if we look at our mole floppy, what we're doing is we're starting with molarity, which is a 1 molar solution of sodium hydroxide, and we have how much volume of the molarity of the sodium hydroxide we used. So molarity equals moles divided by liters. Okay, and we can use that to find moles of sodium hydroxide. Then we need to use our mole to mole ratio. In this case, it's just a 1-to-1. And then finally, we're going to go from moles of acetic acid to find its to molarity. And that's what we're looking for in this problem. Okay, so first step. 1 molar solution equals N over 8.9 milliliters, which we move the decimal 3 times. and we find out we used 0.089 moles of sodium hydroxide. It's just a 1-to-1 ratio. So right down here, where's our 1-to-1 ratio? And we find out that that will give us this many moles of acetic acid. And then finally, when we're down here, we need to go to molarity, and we have 0.089 moles of acetic acid divided by however much we started with, which was 10 milliliters, and that's going to give us our molarity of acetic acid. So that's how you do a titration problem. Okay, so what about if we had like a diprotic or triprotic acid or something with multiple hydroxides? Well, really the only thing that is going to change is just your mole to mole ratio. Okay, what is this? Well, what we're looking at here is it seems to have 1, 2 equivalence points. Well, it is, and that would be something similar what you'd find for a maybe a diprotic acid.